Hello everyone, welcome back to CMPT 456, Information Retrieval and Web Search. It is great to see you again. Today, we'll start a discussion about indexing and ranking. Indexing and ranking is one of the core core functions in search engines. So in this section, we will discuss the ideas behind the indexing documents and how to evaluate queries using documents. Most importantly, we will explain the ideas and the intuitions behind how to rank documents with respect to a query. We know a search engine crawls and stores documents. And then, given a query, a search engine tries to return a list of documents that are relevant to a query. Conceptually, we have a document which may contain the information that a user may be interested in. And then the document is used in answer a user query. In order to answer user query, say the query tropical fish here, we need to extract some features from the document. For example, here there are some features there to represent the topics of the document. And also, we may have some features about the quality of the document, such as whether the document contains enough links and whether the document is up to date. And then, once given a query, for example, the query is a tropical fish here, we try to match the query with the document using those features. And indeed, we will try to calculate a score, which is called a document score, that measures the similarity or the relevance between a query and a document. And then the document can be ranked according to its document stores. That's the overall picture of how a search engine uses documents to answer a user query. Mathematically, a ranking function which matches the relevance between a query Q and a document D can be written in this form. It can be the summation of a set of features fi and gi, and we apply the functions fi and gi on a document D and the query Q. Here, fi and add to fn are a set of feature functions. Each feature fi indicates the strength of a feature in the document D. This may sound a little bit hard to understand. Let me give you a concrete example. For example, one feature could be how many times a word fish appears in the document. As you can see, the larger the number of times the fish appears in the document, then more relevant the document may be related to fish. Similarly, we may get the G1, G2, and the Gn are the similar feature functions on a query. For example, in a query, we may have the corresponding features, say how important the keyword fish is in the query queue. Then, through these ranking function, we measure how well a query and a document match. And given a query queue and a set of documents D1 to DL stored in a search engine, we can rank those documents according to the ranking function Q di using function R. As you can see, for a feature, if the feature is drawn in a document D, fi, the corresponding feature function, will have a higher value. Similarly, If the feature is also important in the query, so GI will also have a higher value. Therefore, the corresponding component GIFI will be large. And if the document and the query match well, that means they are sharing a few features where they have strong signals in both the document and the query. Then the corresponding ranking function will have a high value. Let's take a concrete example. Suppose we have a document here. Suppose we have a document here. Okay. And then, as you can see, we can extract some features here. For example, the feature fish. We measure how important the feature fish in this document as how frequent this term fish appears in the document. Suppose we say it's 9.7 times. Indeed, later on we will explain why it is a fraction, because we need to do a little bit processing on the frequency. So we will get a fraction. But don't worry about that at this time. And similarly, another feature tropical, we can measure how important the feature tropical in the document, say it's 4.2 and so on. Similarly, for query, tropical fish here, we say, oh, indeed, because I see the term fish and tropical in the query, so I know they have more heavier weight on those features. So we have the corresponding feature score for fish and tropical here. And similarly, tropical fish indeed is exactly the query here. So we have the highest value on the feature function. Then indeed we can sum up the products of the features on the document and the features on the query, and then we can get the document score here. And this document score can manifest how well the document is relevant to the query. A simple implementation of this document ranking function is the following. Let the feature fi be whether a keyword I appears in a document. If the keyword appears in the document, then it takes value 1, otherwise it takes a value 0. Similarly, for feature GI, we define that the feature to be whether keyword I appears in the query. If it appears in the query, then it takes value 1, otherwise it takes value 0. Then, given a query queue, which contains a set of keywords W1 to Wm, we try to find all the documents that contain all the query keywords W1 and Wn. Why? Because if we look at the document ranking function here, because the document ranking function is that on all the possible words, we calculate the sum of the products GIQ FID. And then if a word I does not appear in query Q at all, GIQ will be 0 in our simple implementation. Therefore, those terms we do not need to be buttered. We only need to worry about those words I such that GIQ is 1, meaning the word appears in the query. In such case, we just need to sum up those FID, meaning whether the document appears in whether the word I appears in document D. Therefore, what we really want to do here is that, well, we just say, indeed, the document ranking score of a document D is that among all the keywords in the query, how many of them are indeed contained by document D. Then, a natural idea to implement this function is using one thing called inverted index. This is an idea about inverted index. Suppose we have 4 documents, S1, S2, S3, and S4 here. Each document contains one sentence, like this. Then we can have all the words here. For each word, we record in which document the word appears, no matter how many times the word appears in the document. For example, here we look at the word fish. Because we know fish appear here, fish appear here. So similarly, we say the fish indeed appear in all the documents. And indeed, you see, in some documents, the term fish may appear multiple times. For example, here in document S2, the term fish appears twice, but we only care whether the term fish appears or not. We do not care how much it is appear, how many times it appear. That's the simplest inverted index we have. Arguably, a term appearing frequently in a document may be more important. It may capture the topic of the document better. Therefore, we want to keep the information about the frequency. Then we can add the count information into the inverted index. Well, in such a case, in each post here, we record not only the document ID, just like this one, the number 1 here, not only the document ID, but we also record the number of times that this term appears in a document. For example, here, it means the term fish appears twice in document 1. So this adds a little bit more information to our inverted index and provides more information for the later ranking and indexing. Indeed, we can even go further. We can add not only the count information, but also the position information. We record for a document not only how many times this word appears in document. For example, fish appears twice here in document 1, as we said here, but it also records the position. 2 and 4 means that the word fish appears in the 2nd place and the 4th place in this sentence. Why the add position information would be useful? Let's look at that. First, we can use the position information to find phrases. For example, if we want to find whether the document contains a phrase called tropical fish, indeed, it is very easy. We just aligned the tropical fish, the 2 inverted lists here. And then we see here, because both appears in document 1 and tropical appears in position 1, fish appears in position 2. So we know we have an instance of tropical fish in document 1 here, S1 here. Similarly, we can identify those occurrences of tropical fish in document S2, indeed twice in S2, and also S3. So now let's formally introduce the idea of inverted indexes. An inverted index is essentially a term and the corresponding list of documents containing the term. So we call the set of terms as the dictionary. Essentially, this is something like you look at the dictionary physically. It contains a list of terms, and for each term, we have the list of postings, which represent the information about which documents contain the word and also more information can be attached to the posting list. How to build such an inverted index? There are several ways to build such an inverted index. One way is that we can use the so-called bracket sort-based indexing. The idea is that, well, the whole set of documents may not be able to be fit into main memory. So in order to be efficient in I/O, let's divide the text collection into blocks such that each block can be held into main memory. Then for each block, we can sort the term ID, document ID pairs in the block in main memory. And then we store those intermediate sorted results on disk. Then we merge all the intermediate results into the final result. Let's take a concrete example. Here, as you can see, we divide the whole set of documents into blocks such that each block can be held into main memory. Then for each block, once it is loaded into main memory, we can easily process its postings. We can produce the posting list for the documents in this block in this way. And then after we process all the documents in blocks, the next thing is that we will have several posting lists, and we need to merge them into one posting list like this. So this is a merging task. So the algorithm works as follows. We just iteratively read all documents in blocks, and then for each block, we do the inverted list, and then we write corresponding inverted list of the block into disk. And then at the end, we merge all the blocks into one final inverted index. Now, we need a little bit time complexity analysis here. As you can see, we need the time cost of these sort-based indexing is in the order of t log t. Why? Because here, t is the maximum number of term ID, document ID pairs that can be held into main memory. Okay, and then because we need to sort all the document the postings and merge them, indeed we need this t log t to do this. This is a theoretical bottleneck here because we need to sort the term ID, document ID pairs within a block so that later on we can merge them. However, in practice, the I/O is always most costly because we know the disk I/O can be orders of magnitude slower than the main memory processing. Therefore, a lot of time indeed is spent in parsing the documents and also the final merge step. But wait a minute. Indeed, here we have made one assumption. What's the assumption? We assume that we have a dictionary which can be held into main memory so that when you get the term ID, you can look at the memory, look at the dictionary and get the term ID and for each document. Well, this assumption may not hold all the time because if you have a large collection of documents and there are many terms there, indeed the dictionary can be too big to be put into main memory. How can we handle the situation like that? One idea is to use this single pass in main memory indexing. The idea is that for very large text collections, the dictionary may not be held into main memory. Then we can create a dictionary for each block using a hash function. And then we can add a posting directly to its posting list. We don't store the posting of the item, term ID, document ID pairs in blocks. For example, this is the algorithm. Well, we load the file into main memory. Whenever there is a space, we just do the following. We look at the next token. If the token is not in dictionary, and then we create a new entry into the dictionary. And otherwise, you just get the corresponding term or token. If the term is already in the dictionary, you just get the dictionary token. If the dictionary is full, meaning if there's no space to hold these postings, then you can double the size of the postings and add the corresponding item, term ID and document ID pair into that. And then you sort the terms before posting these are written into disk, and then you write the whole block into disk. So you accumulate all those dictionaries on disk, and you don't need to be confined by the assumption that the whole dictionary may be held into main memory. Indeed, as long as the dictionary of the block can be held into main memory, that's fine. Otherwise, you just maintain the dictionary on the fly. In such a case, the time complexity is in the order of T, because you can index the collections of any size as long as there is enough space available. This is the advantage of the single pass in memory indexing approach. However, this time complexity analysis is based on one important assumption. It is that the number of terms is much smaller than this T, where T is the maximum number of term ID, document ID pairs that can be held into main memory. In many situations, this assumption indeed holds well. But in the extreme case where each term in the block is new, then this assumption doesn't hold. In such a case, the complexity is still in the order of T log T, which is the theoretical bottleneck. You may wonder, indeed, how those commercial search engines handle many documents and many queries. Indeed, they use one thing called MapReduce to process those documents. In case you do not know what MapReduce means, let me give you a very quick introduction to the MapReduce mechanism. A MapReduce is a two-step, two-phase process. In the mapping phase, each mapper independently processes a chunk of data and generates a set of data entries with keys. In the shuffling step, which will be done automatically by masters, all the data entries generated by mappers will be shuffled and then assigned those data entries to the same reducers. In other words, all the data entries with the same key will go to the same reducer. Then, in the reducing phase, each reducer independently processes a chunk of entries assigned and generates the output. Why MapReduce, you may ask? When a search engine has to process many documents, indeed, it is almost impossible to avoid some errors from happening. Therefore, a MapReduce mechanism needs to guarantee that it is highly fault tolerant. This is the major idea why MapReduce is so popular. MapReduce has a very nice property called idempotence. It is that if the mapper or reducer is called multiple times on the same input, the output will always be the same. In other words, if the mapper or reducer goes wrong, we can just restart it and run the same program on the mapper or reducer again, and it does not affect the output. This is a very nice property of fault tolerance. The MapReducer works as follows. The input is fed into mappers, and then mappers produce the data entry using some key. I will show you one example to get better understanding in just 1 minute. And then at the shuffling stage, which is automatically done by the master, and those data entries will be shipped to the reducers in the way that all those data entries with the same key will go to the same reducer. And then the reducer will independently process all the data entries assigned to it and then produce the output. Let's look at one concrete example. It is using the MapReduce to construct the inverted index. First of all, you have a set of documents. You have those documents to be passed by your parser. And then the parser will produce the corresponding key value pairs. The key will be the word. The value will be the document ID. Or you can append more information like the location, the frequency, all those information in the pair. And then these will go to the reducer, and the reducer collects all the key value pairs. That means all the key value pairs of the same document using document as the key, and then convert them into the postings. Let's look at the code a little bit. As you can see, the mapper generates pair, the word and the document and its position. And the reducer generates a posting list for words. Here, all the pairs, word, document, position pairs, go to the same reducer if they are about the same word. Therefore, the reducer only needs to sort all the document positions according to the document ID and position. Then, naturally and straightforwardly, output the list, posting list. The code works as follows. The maps stage does the following. It keeps consuming the input, and once it gets a document, it looks at the number of words in the document, and then start from position 0. And then it passes the document. And then for each word in this token, it emits the word W, which is the word itself, and also the document and the position. And also, it maintains the counter to trace the current position. Iteratively, we do this until it finishes parsing one document, and then iteratively in the outer loop to continue until it finishes all the documents assigned to this mapper. The reducer collects all those key value pairs where the key is the word. Because of the MapReduce mechanism, it ensures that all the pairs having the same key, meaning having the same word, will go to the same reducer. Therefore, the reducer can only do the following. It gets the key, which is the word, and then it writes the word. Then it keeps getting all those pairs as from the input to the reducer, and then it just look at the postings and then encode those postings and write that on the disk. Then that makes the complete list of word postings for the specific word. Is that simple? Yes, indeed. The beauty of MapReduce is that the logic is very simple, and you rely on the system to do the shuffling and also the resource management. Well, if a mapper goes wrong, never worry. You can restart the mapper again and feed the mapper with the same set of documents. Although the mapper may produce multiple such key value pairs to the reducer. However, those pairs will contain the same word information and document and position information. Those redundancy can be processed in the reducer. And similar thing, if a reducer fails, what you really need to do is that you restart the reducer, you run the reducer again, and the reducer still can collect all the key value pairs produced by the mappers about the same key, and then it just sort those keys and the document position information again and produce exactly the same posting for the list for the same word. One interesting challenge here is that, well, a document collection may grow over time. Indeed, as we explained before, a search engine keeps crawling data. Therefore, it has more and more updated data documents being added into its collection. Therefore, a search engine has to maintain the collection of the text and also maintain the corresponding inverted index. This leads to the problem of incremental maintenance. In the incremental maintenance context, the text collection may have changes in two types. The first is insertions, meaning new documents being added into the collection. The other is deletion, meaning some documents may be removed. One idea to handle incremental maintenance is that we can build multiple inverted indexes. The first is that we maintain the data D as two parts. For example, one is the original data, one is the new data. Then we build index I for D1, and we build delta I for the delta data. And we only need to merge these I and delta I. This is particularly useful when the updates come in large batches. For example, you may have thousands or even millions of documents at a time, so that both I and delta I are not small, so they can be easily merged. However, if the input comes in very small batches, for example, just several documents updated at a time, then you may have too many such tiny indexes, and which may be hard to process in a scalable and efficient manner. So this method does not work well if the updates come in small batches. Alternatively, another way to handle the incremental maintenance is to do the result merging. So-called result merging is the following. You build a small index for the new data, but you do not merge these small index into the large index. The new small index can be held in main memory, and thus is easy to update. And then when you evaluate a query, you evaluate the query separately on both the original large index and also on the small index. You merge the results instead of the indexes. And also, you can handle a deleted document by maintaining a deleted document list, so that you from that list you retrieve that a specific document has been deleted, so that it should be removed from the result set. As you can see, in this way, because the result set is typically small, so result merging typically can achieve good performance if you have many small indexes, meaning many small batch updates. Well, still, using too many indexes may slow down the query processing, and using too few indexes may slow down the index construction throughput due to the excessive disk traffic, because you need to access those indexes and each one will be still big. So in practice, many search engines can adopt this geometric partitioning approach. In this geometric partitioning approach, we divide the dataset into multiple layers. The smallest and the highest layer is called I0. It contains as much data as possible can be fed into main memory. That means this is the set of documents that can put into main memory. We can use it to produce the query results quickly. The next level is L1, which contains R times as much data as L0. Continuously, we can do the R2 and R3 and LM. LM in general contains between n times r to the power of m and n times to the power of r to the power of m plus 1 bytes of data, where n is the main memory size. If r equals 2, then this is called the logarithmic merging and can hold 1,000 times of the original main memory size. Suppose we use 10 indexes. This is the algorithm of logarithmic merging. Essentially, you start with this Z0, you merge the Z0 with a token. And then when Z0 meets the memory size, then you try to load the index from I, and then you get this Zi plus 1 to merge the indexes. So you can see, whenever a new token gets into the system, we try to find a home for this new I token. We start from the main memory, 1 Z0, and if the Z0 has space, we will locate this token there. Otherwise, we just move down to the different levels until this level has the space, and then we just add this token there. So far, we discussed how to build a posting list. However, only the posting list itself may not be able to answer any query. Indeed, we need another part of the inverted index, which is the vocabulary, meaning the inverted lists themselves cannot answer queries. We need the vocabulary so that we can find the inverted list for a particular term. A naive method is that we can store each inverted list into as a separate file and then name after the term, so that whenever you see a new term, you just open a file using the term as the name of the file. However, just imagine in a large document set, you may have millions or even billions of terms. Then you cannot have billions of files in the system efficiently. Most of those document posting lists can be very short, because remember, we talk about the frequency of terms in document collections. We say half of the words may appear only once in a set of documents. Therefore, most of those inverted lists, those posting lists, can be very short. This creates a huge problem for file systems in commercial computers, because there are no file systems can handle such a huge number of files in an efficient way. We need to find some other way to handle the vocabulary efficiently. One idea is that we can use dictionary as a string. For example, we can use 20 bytes for a term, 4 bytes for document frequency, and 4 bytes for a pointer to posting lists. In such a way, if we store 400,000 entries, we need the 400,000 times 28 bytes, which is 11.2 megabyte. Why 28? Because we have this 20 plus this 4 plus this 4. We have this 20 plus this 4 plus this 4, so 28. But indeed, many words are much shorter than 20 bytes. If we use the fixed length for a term, we waste a lot of space in storing those entries. One idea is this inverted file. Essentially is that we have all the inverted lists stored together in a single file. So in such a case, a vocabulary contains a lookup table from the index terms to the byte offset of the inverted list in the inverted file. If the vocabulary is too big, we can use a tree-based index structure so that we can facilitate the search quickly. Let's look at an example. Suppose on an average, a term has 8 bytes. We only need 400,000 terms times 8 bytes, which is 3.2 megabytes to store the terms. Then this is a huge saving than these 11.2 megabytes. Of course, we still need to search the pointers, so we need, this is the address space for those terms. So if we use the binary coding for that, we need log2, 3.2 times 10 to the power of 6 is 22 bits, which is about 3 bytes for each term pointer. Sum up these two numbers. In total, we need 400,000 entries. Each entry, we have these 4 times 3 times 8, which is 19 bytes. And the total will be 7.6 megabytes for the whole dictionary. Here, we save 3.6 megabyte space. If you don't remember why we need this 4 and 4, and just remember we need 4 bytes for document frequency and 4 bytes for pointer to posting lists. And these 8 bytes referring to this average term length. So this is one example. Suppose we have the postings here. We have the frequency information. We have the posting pointer. We have the term pointer. So the layout will be like this. Okay. We may even save more. We may do the block storage, meaning we can group the terms in the string into blocks of size k and keep a term pointer only for the first term of each block. Essentially is that we may pack all those terms in this block into one block. We only have one pointer here to go there instead of having all the pointers. That will give us further saving. In such case, in each block, we can enumerate k minus 1 pointers. When k equals 4, meaning we can save 4 times 1 times 3 equals to 9 bytes. We need k bytes for the length of terms. When this k equals 4, which means 4 bytes. And when k equals 4, the saving 5 bytes per block. Total saving will be about 0.5 megabyte. You can see the efficiency of the saving indeed depends on the parameter of k. Well, the larger of k will give us more saving, but of course, the larger of k will also slow down the search within the block because we need to do the binary search on those in terms in order to decide the exact location of the term in the block. So in practice, typically we set a k to a large number like thousands in order to achieve the scalable performance. We can do a little bit further, encoding to save space. The idea is that we can do front coding, meaning we code each consecutive entry in an alphabetically sorted list, share the same prefix. The same prefix can be omitted. For example, here, because we have the terms like automata, automate, automatic, and automation. So we can ask them to complex to share the prefix, say, automate. And that can be coded as automate here. And then we say this star meaning this is the first term concatenating after this t. So we have A here. And then the next one will be changing this position to E. And then and so on. This will save about another 10% of the original size in many cases. Okay, in this first part of the indexing and ranking, we motivate the need of building the index to help matching documents and queries. We explain the general idea behind the matching mechanism and also how we can measure the relevance between a document and a query so that we can calculate a document ranking score for the later ranking those documents with respect to a query. And then we discuss how to build an inverted index, different methods by different assumptions. And we introduce one important mechanism called MapReduce, which can allow us to handle a large amount of data in a distributed cloud-based environment. And then we talked about different ways to encode the vocabulary so that we can save space. That's all for this part. And later parts will also give you more information on how to use those indexes to answer queries. Thank you. See you next time. Bye-bye.